Here's a problem where we're mixing two solutions containing salts, and they're asking us to calculate the concentrations of ions that form a precipitate at equilibrium. They give us some big hints here. First of all, they tell us what the potential precipitate is, lead 2 chloride. They even give us the KSP value, which will be useful later on. Secondly, unless they tell you otherwise, or unless they're specifically asking whether or not a precipitation occurs, it's safe to assume that a precipitation happens. So let's note that. Assume that precipitation happens in a precipitation problem, unless told otherwise. Next, let's just write down some basic information that they gave us. They give us a volume and a molarity. I'm going to translate the number of milliliters into liters. And I'm going to indicate that we're going to multiply volume times molarity in order to get number of moles. Also, this is an important point, but they're not trying to trip us up on it. The implied subscript for lead within lead 2 nitrate is a 1. If that weren't the case, we couldn't just multiply across. But if I take 0.05 liters times 0.11 molar, I get 0.0055 moles of lead 2 ion from the solution of lead 2 nitrate. Next, let's note the other solution. 50 milliliters, or 0.05 liters, times a concentration, in my case, of 1.6 molar. Noting once again that the subscript for the ion we're interested in is an implied 1. If I just multiply then, I get 0.08. I'm going to add an extra 2 zeros just so it looks like we're working, it's easier to compare the two numbers. So we've got a certain number of moles of lead 2 ions and a certain number of moles of chloride ions in the salt. Next, let's consider the reaction to completion. Knowing that we have these 2 ions, and knowing that they form a solid salt with a pretty small KSP value on the order of 10 to the negative 5th, that means the presence of these 2 ions in solution will, the vast majority of them will form a solid salt. So we've got lead 2 ions floating around along with chloride ions. Let's note the number of moles before, which we've calculated here and here. Let's just write those down. For lead, it's 0.0055 in my case, moles. And for the chloride, 0.0800 moles. The solid drops out of all tables. We want to work our way down to an afterwards number of moles for each of the 2 ions. And just like any reaction to completion table, one of the reactants goes away completely. And it's going to be the one that has a smaller number of moles. But there is something to notice. They're being a little bit tricky this time. There's a coefficient 2 here. So I want you to follow the math carefully. If the lead entirely reacts away, we see a reduction of 0.0055 moles of lead 2 ions, and that gives us 0 afterwards. The chloride ion will also go down in concentration, but because of this coefficient 2, it's going to go down by 2 times 0.0055, which is or Hw29. That gives us a number of moles of chloride of 0.069 moles. That's really important. That coefficient 2 affects how many moles of chloride go away. And be sure to note that in your calculations. Okay, now we've got, at the end of a reaction to completion, we have a certain number of moles of both lead-2 ion and chloride ion. Well, we can write an ice table with the salt that forms. Some of it will dissociate, not much of it, but some of it will. And since we know the KSP value, we have an idea of the extent to which it does. When working in ice tables, remember, it's worked out in units of molarity, not moles. So we'll pull down the numbers that we had worked out. In the case of lead-2 ions, at the end of the reaction to completion, we had 0 moles. But then to get a concentration, we have to divide that by the total volume. Well, the total volume can be found by adding the individual volumes of the two solutions that were originally mixed together. So 0.05 plus 0.05 will give us 0.1 liters. So the chloride ion, which we found that at the end of the reaction to completion, we had 0.069 moles. If we divide that by a total volume of 0.1 liters, we get 0.69 molar. And we can write that down as well. And then we just fill out the ice table like you would any ice table, noting once again that there's a coefficient 2 for chloride. And at equilibrium, get this shifted up, our KSP expression can be found by multiplying those ions, concentrations together, and make sure that you raise it to the power of the coefficient. That's important. And if we plug in numbers, we would get x times the expression 0.69 plus 2x all squared. Well, I think we're going to be safe to make the mathematical assumption that 0.69 plus 2x is roughly equal to 0.69. We'll set all of this equal to the value of KSP they had originally given us at the beginning of the problem of 1.6 times 10 to the negative fifth. And if we divide that out, x works out to be 3.36 times 10 to the negative fifth, a really small number. So at equilibrium, we've got a concentration of lead equal to x and a concentration of chloride equal to 0.69 plus 2 times x, which if x is really small, then it's roughly just 0.69. So at equilibrium, our concentrations are 3.36 10 to the minus fifth molar in the case of lead-2. And in the case of chloride, I'll write this out just to illustrate it. If I plug in 0.69 plus 2 times a really small number, 3.3610 to the minus fifth. If you work that out on your calculator, you get like 0.69000001. It's still roughly 0.69. So that value of x is indeed negligible compared to the concentration at the beginning of the equilibrium. And that's what I would fill in for the answers. This was a deceptively long problem. There's a lot of work to it. But hang in there, and we'll make it through solubility.